Since we've talked about orbitals as probability distributions and electrons, we're almost ready to start putting electrons into these orbitals. Before we get into electron configurations, however, there are a few other concepts we need to touch on. First, we need to talk about this idea of electron spin and the Pauli exclusion principle. The concept of electron spin was developed to account for details of emission spectra of atoms. It represents a fourth quantum number, the electron spin quantum number, m sub s. Electrons have magnetic moments with two possible orientations when placed in a magnetic field. It was postulated that electrons have two spin states producing two oppositely directed magnetic moments. So electrons can be spinning in one of two opposite directions when placed in a strong magnetic field. They can either be aligned with the magnetic field plus 1/2 or against the magnetic field opposite minus 1/2. This is important because, according to Wolfgang Pauli, in a given atom, no two electrons can have the same set of 4 quantum numbers, which means that they can't have the same n, l, m sub l, and m sub s value. Since electrons in the same orbital have the same n, l, and m sub l value, they have to have different m sub s values if they are in the same orbital. This is the Pauli exclusion principle. Since there are only two values for m sub s, an orbital can hold only two electrons, and those two electrons must have opposite spins. Now, when we look at hydrogen, we only have one proton and one electron. We have no electron-electron repulsions to consider. So in hydrogen, as a model, all orbitals at the same principal quantum level are degenerate or equal in energy. So our 2s and 2p orbitals for the hydrogen model are at the same energy. The 3s, 3p, and 3d orbitals for hydrogen are at the same energy. Notice energy increases with increasing principal quantum number. So something in a 2s orbital is higher in energy than something in a 1s orbital. Now, when we look at polyelectronic atoms, atoms with more than one proton and more than one electron, so something like helium or something with a greater atomic number, we have three energy contributions to consider. We have the kinetic energy of electrons moving around the nucleus, as we have in hydrogen. We have the potential energy between the nucleus and our electron, as we do in hydrogen. But we have a third energy contribution in polyelectronic atoms, which is the potential energy of repulsions between electrons to consider. Now this leads to an electron correlation problem. It's possible to describe the helium atom in terms of quantum mechanics, but the Schrödinger equation cannot be solved exactly. There's a problem with calculating electron repulsions. Since the electron pathway is unknown, electron repulsions cannot be calculated. This is where we run into our electron correlation problem. This occurs with all polyelectronic atoms, so we must make approximations in order to solve Schrödinger's equation for polyelectronic atoms. We treat each electron as if it's moving in a field of charge that is the net result of nuclear attraction and the average repulsion of all other electrons. If we consider the sodium atom, we see that the outermost electron feels the pull of 11 protons in the nucleus, but in between that outermost electron and the nucleus, there are 10 other electrons. Because electrons are all negatively charged, there will be repulsions between electrons, and the result will be a shielding of the outermost electron from the nucleus. Overall, the result is the outermost electron does not feel the full effect of the nucleus. It is shielded from the nucleus. So our picture for polyelectronic atoms is hydrogen-like. The orbitals have the same general shapes, but the sizes and energies are different because nuclear attraction and electron repulsions are different. We see a big difference with orbitals in the same principal quantum level. For hydrogen, all of our orbitals are at the same energy level, again, are degenerate. For polyelectronics, our principal quantum levels vary in energy. The 2s electron penetrates to the nucleus more than one in a 2p orbital. This causes an electron in a 2s orbital to be attracted to the nucleus more strongly than an electron in a 2p orbital. Thus, the 2s orbital is lower in energy than the 2p orbitals in a polyelectronic atom. Overall, the 2p orbital seems to have a probability curve closer to the nucleus, but the small area of probability which is very close to the nucleus for the 2s orbital is very significant. The 2s electron is said to penetrate to the nucleus more than a 2p electron can. This penetration effect causes the electron from a 2s orbital to be attracted to the nucleus more strongly. The 2s orbital is therefore lower in energy than the 2p orbital. We see a similar result in other principal quantum levels. If we compare the 3s, 3p, and 3d orbitals, the 3d orbital overall appears to have a larger radial probability closer to the nucleus, but the 3s orbital has a small area of very high probability, which is more significant and penetrates the 3s electrons closer to the nucleus. The 3p also has this penetration shell, and so the 3s orbital is lower in energy than the 3p orbital, which is lower in energy than the 3d orbital. The more effectively an orbital allows its electrons to penetrate the shielding electrons and be close to the nuclear charge, the lower the energy of that orbital. Overall, we see that the order of energies of orbitals in the first three levels for polyelectronic atoms follow. 1s is lower in energy than 2s because it's lower in principal quantum number. The 2s orbital is lower in energy than the 2p orbital because of the penetration effect of an s orbital compared to a 2p orbital. And in the third principal quantum level, we see s is lower than p, which is lower than d, again because of the penetration effect.